Hello everyone, welcome to the second lecture about operating systems. In this lecture, we are going to continue talking about different functionalities and different tasks that operating systems do. In particular, we are going to talk about file management and directories that an operating system takes care of. And we're also going to talk about parallel computation. And at the end, we will talk about virtual machines, which using them you can have several operating systems on your machine. So let's recap first. An operating system was a computer program that controls the hardware, has access to the hardware, and lets different users or different programs run at the same time on your computer. So it's the intermediary between the computer hardware, being CPU, memory, I/O devices, and the software that wants to use that hardware to complete its task. Computers have different storage media and can store the data in many different ways. In general, the memory of a computer is divided into categories. The first one is called primary memory, and the second one is called secondary memory. Primary memory holds only the data and the instructions for the processes that are running. And primary memory consists of RAM, which is also called the main memory, and also caches and registers. So you have seen that, for example, in the assembly program, it was most apparent that when we would run the program, the registers and the RAM would contain the data that the process needs for its execution. But we have not yet seen cache. Cache is used to fetch the data from the secondary memory and store it so that it is closer to you, and whenever you want it, you can access to it faster. You can think of it, for example, as your disk. You can imagine you have a bookshelf on which you have many books, which you might not always need to. But on your desk, you can place several books and they are closer to you, so you can reach them faster, but your desk has less capacity than your bookshelf. So caches are like that. So they have less capacity, but they are faster and also more expensive. Secondary memory is all data storages that is not currently in a computer's primary memory. All storages that is attached to your computer and saves the data permanently. So the data that is written to secondary memory, for example, on hard drives or CDs, DVDs, magnetic tapes will not be deleted even if you turn off your computer. But the data which is stored in primary memory, for example, your RAM, will always be deleted as soon as you turn off your computer. In this diagram, we can see how different storages are compared to each other regarding their size and their cost and speed. So the fastest, the smallest, and the most expensive memory in your computer are the registers. For example, we saw in case of MIPS processor that we worked with, we had only 32-bit registers where each of them contained 32 bits. So this becomes 1 kilobyte of data only. After this comes cache, which is still expensive, but less expensive than registers, and it is fast and yet small. And then comes your RAM that in current computers, it can be like as big as 16 to 32 gigabytes, but still it is much smaller than your hard drive. So these are these first three ones are the primary memory that are used for processes that are running on your system. After that comes the secondary memory, for example, hard disk, and offline storage is different kind of storage. For example, when you store your data on a server somewhere else outside your computer. And these kind of data these kind of memories are huge. So when we work with computers, we don't directly access the memory of the computer, and we don't know what are the details there. What we work with is computer files. An operating system is the one that actually hides all the physical details of the storage devices and defines a logical storage unit, which is called a file. A file is the smallest unit of secondary storage. So we don't have direct access to RAM or cache or registers. We just read or write when we work with the computer to the secondary storage. A user only works with secondary storage. A user cannot write data to secondary storage unless that is written to a file. And there are, as you've seen, of course, there are different types of files in your computer, and different types store different data. For example, we can have text files, spreadsheet data, music files, video files, and in each type we can have, again, different categories. For example, for music, there are different extensions of files. And there are several operations that one can ask an operating system to do when it comes to files. For example, we can ask the operating system to create a new file, to read from some file, to write to it, delete it, open it, close it, etc. All these are things that the operating system does for us. So again, I should emphasize that we don't directly work with the hardware of the computer. It is the operating system that takes care of all these manipulations that we need. And for these purposes, we use system calls. And for each file, there are several attributes that an operating system has to store and keep track of. For example, its name, identifier, what kind of type it is, where is its actual physical location, how much is its size, and how it is protected, who can write to it, who cannot, and what time it was created, modified, and which date, and the user information. So here you see a simple Python program in which a file is accessed, and we can try. I copied those lines of code here. So first of all, I want to open a file, and this file already exists in the directory, the same directory that my program is. So this is the program I'm working with, and this is a simple text file. I have written just arbitrary text here. And what I want to do is to open this file. So whenever you want to use a file, you always have to tell the operating system to use it. So in Python, we simply write open, and we pass to it the address of the file, which contains its name and its address if it is stored in a different location than the code. And then after that, we can read from the file. So in this line, the whole content of the file is read, and it is given to the print function. So we expect it to print the function. And then we close the file. All these will be translated to system calls that are issued to the operating system. We don't see the actual system calls. If we were doing assembly language, we would see the exact system call and its system call number. But here in Python, we are at a higher level. So when we finish, we close the file. This is like releasing this resource. And after that, we try to write to the file and want to see what happens. But first, I want to comment out this line of code. So I run it. So you see the whole content of the file, which was just a single line, was printed out. Now I want to uncomment this line, save and run. So you see that it is first printing out the content of the file, but it is giving me an error. It says that input output operation on closed file is the reason for the error. So we cannot close a file and then write something to that. So there are several file operations that are possible in any programming language, and these are these basic operations. There are also more operations that can be implemented using these fundamental operations. So the operating system has the responsibility of taking care of the file, managing when they are opened, when they are closed, what are their attributes, who can access to which file, and so on. And besides files, we have the directories, which is a file system cataloging structure. In each directory, there is a set of references to the computer files that are in that directory. So directories like files are logical entities, meaning that they don't exist specifically on the memory of a computer. A file that you see as a single unit might be scattered into several sections inside the memory, but you see it, we as users see it as a unique entity. So this is again the job of the operating system to manage the memory for the users to have at a high level access to files and directories and not care about the physical details of those. So next we want to talk about parallel computing, what it is, why do we use it, and what are their benefits and also challenges. So before we go there, let's first review a little bit what a process is. So we saw that whenever we want to run a program, the operating system must allocate memory for that program to execute and create a process. And we had gone through the life cycle of a process and what operating system does to schedule processes and so on. So here we want to talk a little bit about the memory that a process needs. So a process needs a piece of memory to store the data that it is working with. If you think of the MIPS simulator, we saw that there was a section in which the data was stored for the process. And there was another data which was called the text segment, which stores the code for that process, the code of the program. And then we saw also the line of code that was being executed next was also kept track of. This is called program counter, or PC for short. PC in this context is different from personal computers, which are also called for short PC. And then a process has also something called stack. So you see here, which is used for function calls, and it is also has also another part of memory which is called heap, which we go to the details of it. But this is a heap is any part of memory that is allocated to a process, but it is not data segment or text segment or the stack. The other, what remains is called the heap. So every process will be given some amount of memory so that in it can put all the text of the program. It might be it is actually a binary code when it is translated in terms of machine code, but it is still called text. And then the PC of it and the data it needs, etc., are written to the memory that is allocated to the process on primary memory. So all these will be written to the RAM, which is the primary memory. So Processes that exist in the system might need to communicate with each other. We have seen that we can have multitasking, which means essentially several processes can run simultaneously. And it is possible that these processes need to transfer some data between themselves. And there are different ways to do this. There are different approaches. The first one is called message passing. In this case, the communication takes place by means of messages that the processes send to each other, and they can send it via the kernel. So in this case, you see that process A wants to send some message, so it's write it somewhere in the kernel, and whenever process B wants to access this message, it will fetch it from the kernel. There is another approach which is called shared memory. In shared memory, a specific region of the memory is used for sharing the data, and the processes will write to this place and read from it to exchange information among themselves. So in this case, you see that the kernel is not involved in the message passing. So for message passing, there are different methods. One is called pipes, which is used a lot in Unix operating systems. A pipe will be created calling a function pipe in Unix, and is a kind of connection between two processes or threads. We will talk about threads in the rest of this lecture. And it's a connection with in a way that the output from one process becomes the input to the other one. So here you see two processes. One of them does sorting. So it has an input and an output. The other one wants to do something else. Its job is actually, in this case, to filter some of the input. So it has its own input and its own output. And here, the programmer has put a pipe in between them so that the output of this sorting process will be the input to the filter process. So they basically communicate in this way. So the first user gives some input, some names of some fruits, and then the sorting process will sort them alphabetically and passes them through the pipe to the filtering process, which will filter apple and will return, will write in the console peach and pear. And pipes are like a first in, first out queue, similar to the FCFS scheduling we had seen in the previous lecture. So the first thing that comes in the queue will go out first. So now that we have talked about processes and the memory, memory requirements and their communication and multitasking also that we covered in previous slide, we want to talk about how processing takes place inside a computer. So old computers had just a single processing unit. And the chip speed, we saw that based on Moore's law, doubled every 18 months. So it had an exponential growth, meaning that the transistors became smaller, so they sat closer to each other on the chips, so the data would then need to travel shorter passes, so the computers became faster. But this trend of being faster and faster exponentially actually dropped around the year 2000. So as you see here in this diagram, we can see how fast the computers became since 1970s. We are interested in these blue dots. We show the performance for computers that had we show the performance when we have only a single processing unit. So you see that first it was following an exponential trend, but then it didn't continue that trend. If it would continue, it would go up like this, but it didn't. So this was because of the physical limitations of the transistors and how smaller they could become. They had somewhat reached their margin. So then the question was, how would computers become faster? Was it the end to speed up computers? But the answer is no. So by that time, computers were using only a single processing unit. But what was introduced during that time was that computers would have multi-core processors. For example, in 2001, IBM introduced its processor called IBM 100, which had 2 cores. Cores are processing units. So in a multi-core processor, we have a processor that has 2 or more processing units that work together on the same chip. These processing units are called core. And one core can perform one task at a time, while the other cores handle the tasks, other tasks. So we can process different things at the same time. So here in the right side, you see another multi-core processor, which is called AMD quad core or 4-core, which has 4 cores. And in this picture, you see it's 4 cores. And in between them, there are buses, their memory, and other things that a processor needs. So when we have several cores, we can have parallel computation. It means that we can have a type of computation in which the work or the problem that we want to solve is divided into smaller tasks. And then this work can be done at the same time using our different cores. In this way, the computational speed of the computer is increased a lot. So you see here first, before multi-core computers, we had only serial computing, meaning that we would feed a process to a processor, and we could only have one process at a time. Although we had multitasking and we would benefit when such processes are idle and are waiting for I/O, but still we had just one processing unit. But with multi-core computers, we could divide a process to smaller tasks, and these are actually called threads in operating systems and in computing. So threads are like small processes that divide the work of the process, and then these threads can run on different cores of the computer. For example, here in these 4 cores, we can have 4 threads at a time at most. So let's see in more details what threads are. A process can have one or more threads of execution, meaning that its execution is divided to smaller chunks. You can imagine, for example, we have a final exam that we want to correct using a computer process, and this process divides the work. Imagine, for example, the final exam has 4 questions and the process creates 4 threads, and each of them is responsible in just correcting one of the questions of the exam. Or there are many examples that processes can benefit from using threads in them. For example, imagine you have a big for loop, which is going to have like 1 million iterations. You can divide the work to 4 or 16 or whatever number of cores that you have, so that this will take like 1/4 of the time or 1/16 of the time, depending on the number of cores that you have. So threads share some data with each other. For example, they share their heap and their data, and they share the text segment, which is the process code, because they are going to run the same code, but maybe different parts of it or different iterations of it. But there are some things that are specific to each thread. For example, each thread has its own stack, and it also has its own program counter or PC, because different threads can execute different parts of the program. So they are given this freedom so that they can move as freely as they could, and they speed up execution of the whole program. So these threads execute concurrently on the cores. So if you have 4 cores, you can have 4 threads at most that run at the same time. You can have more threads, but they don't run at the same time. There will be some sort of multitasking between them. So threads will speed up a lot your computer, but they come with their own challenges. For example, one of the very famous challenges is called data race. A data race occurs when you have a piece of data which is shared and different threads want to access it at the same time. And it is called a data race when at least one of the threads want to write something here. So imagine the example in which we would like to use threads for correcting the exams. Imagine that we have 4 questions and 4 threads that each one wants to correct one of them. So your grade can be a resource that they share. So before they execute, the grade is 0 because they have not yet corrected anything. So different scenarios would happen when we have several threads in this case. So one scenario is that all of them read your grade first, it is 0, and then they see that you have answered correctly to the question that they are responsible for correcting. So then they want to add your grade by 1. So the first thread computes 0 plus 1 is equal to 1, and all the others would the same. Then they write your grade. So all of them in this case would write 1, although your grade would have been 4. So this is something problematic. The problem that happened here was a data race, meaning that threads were reading and writing at the same time. So this resulted in a wrong grade for you in this case. So a correct approach would be that each time they want to update your grade, they get the latest value, the result of the previous threads, and then they increment that by 1, for example, in case you have answered correctly. So for this purpose, there are several things that operating system and programmers need to take care of so that the data races don't happen. In order to solve this problem, we first need to introduce something called critical section. When we have concurrent accesses to shared resources, we can have unexpected or wrong behavior and wrong results, as the example that we saw about correcting your exams. The part of the program in which the shared resources are accessed must be protected. For example, your grade in this example must be protected so that the final grade which is stored for you is correct. Such parts of the program that are shared and have to be protected are called critical section. And for protecting critical sections, operating systems use synchronization mechanisms. And we will see what are the different synchronization mechanisms. To protect data races in general, there is a property that needs to hold, and it is called mutual exclusion. Mutual exclusion means that at most one thread at a time can be in a critical section. For example, one thread at a time can write to the shared resource. So here we want to introduce two different synchronization mechanisms. The first one is called mutex or lock. This mutexes use a locking mechanism. It works in this way. So imagine this is the shared resource that you want to protect. You will have around it a mutex or some sort of lock. So whenever a thread wants to access this shared resource, it will lock it, so other threads cannot access it. For example, the first thread that wants to correct a question, one of your questions in the exam will read your grade, it is 0, and then it will increment it by 1, and it will write 1. In the meanwhile, it will not allow any other thread to update your grade. Then after a thread finishes its work in critical section, it will release the resource. So then releasing happens, and then the next thread can come and do its work. So we have some sort of key, and a thread uses this key to unlock the resource, and when it is using it, it locks it, and whenever its work is done, it will again unlock and let other threads to use it. So in this case, we have mutual exclusion, meaning that there will be just one thread at a time using that shared resource. Another mechanism which is offered by operating systems for synchronization is called semaphore. Semaphore uses a signaling mechanism. So in this case, again, we have a shared resource to which different processes or threads want to have access. So it works like this. A semaphore has two functions that are called wait and signal. First, when a process comes and you use this shared resource, it has to call the function wait. If there is another process or thread that is using this shared resource, the first process will be blocked. It will wait here. And the other process, imagine process 2 in this case, was using this shared resource. Whenever that process is done using this shared resource, it will call the function signal. Then it is like releasing this resource. So when it releases it, it will allow the first process that was waiting to come and use this process. So there are these two mechanisms which allow the operating systems to protect shared resources. Okay, they are very good. They allow us to have protection for our resources, but there might be a problem. So, for example, one of these problems, which is very famous, is called the deadlock. A deadlock can be caused when you have different processes or threads that are using their semaphores in a wrong way, and they are waiting for each other forever. It happens like this, for example. Imagine in this case, we have process 1 and process 2. Process 1 is waiting for resource 2. Process 2 is waiting for resource 1. And we have two resources here. Each of the processes has taken one of the resources and is waiting for the other resource because they need both resources for some reason. Imagine an example. So we have a spoon and a fork, and we need both of them to eat lunch. And we have two people. One of them is taking the spoon and the other one is taking the fork. The first one cannot eat because it is waiting for the fork, and the second one cannot eat either because it is waiting for the spoon. So we have kind of a circular waiting, and no one of them can execute, and both of them are blocked waiting for the other. So this is a problem in synchronization, and the programmers that use semaphore need to take care of this when they are programming to make sure that their program will not have deadlock. So we have so far talked about different functionalities of operating system. Now we will continue with a different term called Virtual machines give virtualization of a computer system. It gives an illusion of having multiple computers on the same computer, and you can the user can have the illusion that they are running different operating systems or multiple operating systems on their systems. For example, you can run Mac OS on your Windows or Linux on your Mac OS or any combination that you would imagine. So in this case, we have the computer hardware at the bottom, and then we have the host operating system, meaning the operating system that is installed on this hardware. And then at top of it comes something called hypervisor or virtual machine monitor that manages these virtual machines. And in virtual machines, we have virtual systems. They don't really exist. We have just a simulation of the capabilities of those machines. And on these virtual machines, different operating systems can run. For example, you see here on this virtual machine, Windows 8 is running, on the other one, Mac OS X, and another one, Linux OS. So it enables you to have several operating systems on a single machine. In order to have this capability, one has to use something called hypervisor. Hypervisor is a kind of emulator that creates and runs the virtual machines. So it acts like an interface between the operating system which is installed on your computer and is called host operating system, and the virtual machines that are used in your system. So the operating system runs on top of the hypervisor, the operating systems that are in the virtual machines, and they have no idea that they are virtual. To them, it seems that everything is real. So here in this picture, you see we have the computer hardware again, and on it some operating system is installed, and on top of it there is the hypervisor which manages all these virtual machines. So in this case, there are two virtual machines installed, and these virtual machines have no idea that they are virtual. To them, it really looks like that they are running on the hardware and they are installed on the hardware. And this is the job of the hypervisor to take care of that. And having virtual machines has several benefits. For example, it isolates and protects the resources. So for example, the resources that virtual machine 1, in this case, has access to will not be accessible by virtual machine 2. And the data and programs are totally separated and they cannot, so it brings a lot of security to them. And also it, of course, enables you to work with different operating systems on your machine. So there are also virtual machines for servers. A single server can have different operating systems and they are run simultaneously and isolated from each other. And it gives the servers the possibility to distribute their resources in a better way, and it is cost efficient. So you don't need to have several servers with different operating systems. Instead, you have just one or fewer servers, but you are still serving different operating systems. There are different virtual machines and hypervisors currently available. One is called VirtualBox, which is an open source hypervisor and was developed by Oracle Corporation. And it can be installed on Windows, Mac OS, Linux, or Solaris. And on top of it, you can have virtual machines of different operating systems. So there will be several guest OSs. The guest OSs are those that are virtual and are not really installed on the hardware of the computer. Another hypervisor is called the VMware ESXi. Before it was called ESX, and it was developed by VMware. This hypervisor is different from the ones we have discussed before. And it is called type 1 hypervisor, meaning that it doesn't need a host operating system. It can directly install and work with the hardware of the computer. And then on top of it, there are, of course, virtual machines. So thank you very much for your attention, and please feel free to ask your questions.